When you impose a holonomic constraint on a system, you reduce its degrees of freedom. For instance, say I have this rigid body that can freely move about in the 2D plane. It has 3 degrees of freedom. Remember that the degrees of freedom of a system is the minimum number, so min number of independent coordinates or variables that are needed in order to specify the configuration of a system or the position of all particles in that system. So for this rigid body here, again, I'll draw my reference frame, so frame A. I need 2 coordinates, so I need an X and a Y coordinate. So X and a Y in order to describe the location of the center. I could also, as we've seen before, use R theta, but here I'll just use X and Y. But then we also need a third variable, which is the orientation. So we have that theta value. So this system, again, it has 3 degrees of freedom, and that's because we need 3 coordinates or 3 variables, X, Y, and theta, in order to describe the configuration or the state of this rigid body. But now let's take that same rigid body, but say that it can only slide along the surface defined by this line here. In other words, I'm imposing holonomic constraints on the system. Okay, so before, when it could freely move about, it had 3 degrees of freedom, X, Y, and theta. When I say that it can only slide along the surface, what I'm saying is that Y is equal to 0, could also be equal to a constant, so say some constant value h, and we're saying that theta is equal to 0, or again, theta could be equal to some constant value. Again, here's our reference frame. A1, A2, 0, and let's say this is X, this is Y, and that is theta, its orientation. Right? So now when I add these holonomic constraints to my system, I only need 1 coordinate to describe the state of this rigid body or its configuration. If I know what this value of X is, I know where all points on this rigid body are located in a 2D space. So in other words, by imposing this, these 2 constraints here, and by saying it's going to slide along a surface, and limiting the degrees of freedom of this rigid body from 3 down to 1. Now you may be asking yourself, how do I know how many degrees of freedom are in my system, especially if I have kinematic constraints? Well, first of all, you should remember that if you have a rigid body or a particle, right, so a rigid body in a 2D plane has 3 degrees of freedom. So say like an X, Y, and theta. And a particle or point mass has 2 degrees of freedom. It doesn't have an orientation, so X and Y. And if you had a system comprised of a bunch of rigid bodies and a bunch of particles, and they didn't interact with each other, you would simply calculate the number of rigid bodies you have, multiply that by 3, plus the number of particles by 2, and you would have the degrees of freedom of the system, so 15. But again, we really haven't seen systems besides maybe the first week or so where you have components that are all freely moving about. Those are not necessarily the interesting, or perhaps better said, the more realistic examples of the types of mechanical systems we work with, right? We work with systems where parts are interacting with one another or they're connected. So let's review some of those scenarios, right? So imagine we have a rigid body or a particle that can only pivot. Right, so in this case here, for each example, either the rigid body or the particle, the mass particle here, each of these systems has now 1 degree of freedom. So adding this pivot point, or what's also referred to as a revolute joint, now that takes your degrees of freedom and changes it to 1. If you have a, say, a rigid body that can either slide along a surface or along some shaft, same thing if you have a particle that can move within a channel. So here's an example, rigid body versus particle. Doesn't matter, in both cases, you now only have 1 degree of freedom in each of those systems. Another common example of a component you might see, maybe instead of something sliding on a surface, you have a disc or a ball that's rolling on a surface. In this case, you have 2 degrees of freedom because you need to know the location of the center of this either wheel or disc, whatever it is. So you need to know where that is in, we'll call this, just draw a reference frame real quickly, in that A1 direction, so we'll call that X. And then you also need to know at what orientation that disc is at. So there you have 2 degrees of freedom. Y is constant, right? That's always going to be equal to R. So that, again, is an example of a kinematic constraint, a holonomic constraint, if you're setting y equal to R or written out in a way that follows the typical form. You write it like this here. So that's and again, another example of a holonomic constraint. You can also generally use your intuition when you're looking at these systems. I mean, you've all had a lot of practice. Even just as you're writing down what the position vector is, you can get a sense of how many independent variables you actually need to describe the, say, state of a rigid body. And you don't necessarily need to think of it as that formulaic. It becomes almost intuitive with practice. For instance, in our latest homework problem set, we had a system where we had 2 rigid links, and you had 2 revolute joints, one here and one here, and then a revolute joint here, and then this, it was connected to a block that could translate or slide along this shaft here. Okay, became quickly obvious just from looking at this that no matter what angle or configuration you try to put these at, right? So put these links at with respect to one another, you will only ever generate movement of this point here in the x direction. So if you know what this magnitude x is, you know, oops, theta 2, you know what the theta values are, or if you know what one of these theta values is equal to, then you know what this distance is here. So if you had just this system, your degree of freedom would equal 1. So if you find yourself throughout the course as we move forward struggling with identifying the number of degrees of freedom you have, just let me know and I can provide some more formulaic approaches to defining the degrees of freedom of your system, especially with these kinematic constraints. But again, you can use these simple rules plus rely on your intuition and just ask, how many variables do I need to actually describe where this thing is? That will tell you the number of degrees of freedom of your system.